Okay, so now we're going to talk about carbonic anhydrase, which is an enzyme used in order to accelerate the hydration of carbon dioxide by activating water. This is extremely important in the bicarbonate buffer system and is used to regulate pH within the body. So to begin, we have here the active site of the carbonic anhydrase, which is a zinc 2+ ion bound to 3 histidines. This is also bound to a water molecule as well. To begin, the first step is the hydroxide ion generation. So we have the loss of a proton or an H+, and this generates a hydroxide ion or an oxygen with a negative charge bound to a hydrogen. This is again bound to that zinc ion here and 3 histidines. The zinc ion and the histidines create a stabilization of the negative charges within this molecule and throughout this reaction process. So the next step is the binding of carbon dioxide to this active site here. So with this hydroxide ion formation, the water molecule that began as a weak nucleophile is now a strong nucleophile. And our carbon dioxide is an electrophile, so a good group for this nucleophile to attack. The oxygen that has a negative charge attacks the carbon of the carbon dioxide, and the carbon-oxygen double bond moves from here onto the oxygen, which will generate a negative charge on this oxygen here. This again is still bound to that zinc ion and the histidines holding it in place. In the next step, we have the conversion to hydrogen bicarbonate. So this occurs with, as we mentioned before, this oxygen is now bound to this carbon, and this oxygen here has a negative charge, the one that is also bound to the carbon. This generates that hydrogen bicarbonate, but this is stabilized and held together through that zinc 2+ ion. In the next step, we want that carbonic anhydrase to return to its original form in order to be reused. And we also want to now access this hydrogen bicarbonate. So to do this, we will regenerate the catalytic site through the release of this hydrogen bicarbonate and through the binding of water, which we can see here. So as this occurs, we have now regenerated our carbonic anhydrase, and instead of releasing CO2 into the blood, we now have generated this hydrogen bicarbonate that will be released and used in order to neutralize or change the pH in the body system. Next enzyme we're going to talk about is enolase, which is an example of a metalloenzyme. This is an enzyme that is used, it's a glycolytic enzyme that is used in gluconeogenesis. And it has an active site that contains 2 divalent metal ions, which are required for catalysis, which you can see here as 2 magnesium 2+ ions. Here we have the beginning of the active site. We have a lysine 345 here, which hosts or will act as a general base. And then later on, we will talk about the glutamate here, glutamate 211, that will act as an acid. So first, this lysine 345 acts as a general base by attacking here this hydrogen and splitting this carbon-hydrogen bond. This will then generate a carb-anion intermediate that is stabilized by those 2 magnesium ions in order to stabilize the negative charges, as we now have 2 that are formed on these oxygens that are bound to this carbon. This is stabilized as a carboxylate and allows for the process of an acid catalyzed reaction from the glutamate 211. So now we have the oxygen will donate a pair of electrons to regenerate that double bond here. This double bond from the carbon-carbon will be moved to this next carbon-carbon bond here, and this oxygen will donate its bond to this hydrogen here in order to generate a water molecule. This water molecule, this hydrogen that was now bound to this oxygen, will donate its electrons to this oxygen here as an acid, which will then, as you can see here, form the final product, which is the phosphophenol pyruvate,